I just tap the down button here. It'll work.
Why is it moving?
Got it. It's all good. All right, let's get started. Thank you to Charles Hendrich, Chris Ruff, and John Sessler. And then part one, the same force that propels a rocket is pushing the universe apart. It's gas pressure, and it's unbound. Hey, this thing's moving. So some fundamentals here, the first and second laws of thermodynamics and the cosmological principle. Here are the parameters we used to develop our model. They're taken from the Planck collaboration, and you'll notice that the critical density is given in units of mass, and that is because this model develops almost all of its total energy as equivalent rest mass. We developed this model at the time of last scattering, and all the baryons were homogeneous and isotropic gas, which we can treat differentially as a perfect fluid. We do that by examining its thermal energy change. We surround each and every atom in this perfect fluid with the same size co-moving sphere, which has thermal energy, which drops as the sphere expands and converts into the radial kinetic energy of free expansion. So there's three sizes of sphere we're going to examine here. First, the small spheres. Any radius from a basketball up to about 0.03 light years, there is no loss to gravity, and all these spheres expand at the same maximum rate, the thermal root mean square speed of their atoms. On the other end, we have the adiabatic sphere, which has a radius of about 10 light years, and all of its thermal loss is reversible gravity uptake. And in between, that loss gets partitioned. That partition looks like this. We have two different expressions here. On the left side, we have thermal loss, which has an exact integral solution for any radius. On the right side, we have the gravity uptake expression, which I couldn't differentiate, so we have to resort to a finite difference method. You'll notice the gravity uptake expression contains a total mass term shown in orange, which in turn has a light energy term shown in red. Okay? Now, red light, that's almost a quarter of the total mass at last scatter. So these small spheres all expand at the same rate. They shrink when they get bigger until they reach the adiabatic radius or endpoint, which conserves total energy within its imaginary boundary. These spheres, these adiabatic spheres as I call them, they all expand at an exact fraction of the root mean square speed. This constant K is zero order in gas density, total mass, temperature, and atomic weight. It's a universal constant. Thermal loss in the adiabatic sphere is exactly 2/3 irreversible out to 7 decimal places. Okay? Now that radial kinetic energy shown in yellow there, that is the numerator of an irreversible repulsive entropic force of nature, which is expressed volumetrically. Okay? So this behavior is entirely scale invariant. These are normalized plots. Doesn't matter how dense that gas is, its thermal loss is always 2/3 irreversible. Line up the spheres and you get the thermal model. A constant times the root mean square speed divided by the adiabatic radius. This model has properties. It is zero order in temperature and atomic weight. Gas density is the only independent variable here, and it is connected to the baryon density by this green accretion term, which is less than or equal to 1. Now, baryon density co-moves with the scale factor, so we can use that instead, and we will. Today, the universe is about 16% accreted, but at last scatter, it was unaccreted. That was a pure gas giving a pure endpoint, which we find from the Hubble constant. When we use the Planck value, it returns an adiabatic sphere about 20 light years across. Entropy increase can be calculated, and it is always greater than 0. This is important. Cold dark matter's radial kinetic energy arises from its own enthalpic loss. Now, I happen to think that it's all cryogenic neutrinos, but there's no numbers, and all I want you to think about here is maybe relaxing that restriction on lepton number conservation that underlies the insufficiency of neutrino density. Light energy shrinks the adiabatic sphere and increases the thermal Hubble parameter. Okay? This is much of the Hubble tension derives from this particular light effect. And we're going to get into that now. Okay, so we have going to compare the thermal and lambda models at the time of last scattering. We have this z-dependent function, and below that we have lambda CDM. They both have a red term, which is light energy. The z-dependent function also has the pure endpoint shown in blue and that green accretion term. Okay, so the green and red terms are connected on the right in the top box there. Here are the numbers. On the left side of this table, we have the research results of two groups, the Reese and Planck groups, okay, and that 8% tension that's bothering everyone. In the center of this slide, we have those numbers extrapolated back to last scatter. On the right side, we have ratios, which I will call slopes. And on the far right, we have the tension between the models, which is about 25%. When we get rid of light energy, most of that tension disappears, it drops to 9%. And when we accrete 16% of the baryons, that tension disappears, and these models give identical results. Well, for starters, the lambda slope is low, okay? And here the reasons are shown on the far right, those green and red terms, that's why. Now this is going to be controversial. The Planck last scatter value, in my opinion, is also low. And the correct value, I believe, is 35% higher. And see on the far right side, those green and red terms, it's low for the same reasons. Both lambda CDM slope and the Planck values last scatter Hubble parameter are low because they neglect entropic force. And in this public forum, I asked the Planck collaboration, where is your last scatter entropic force term? All right, we're going to move on to dark energy, and we're going to discuss the tension between these models over the entire Z domain, 0 to 1089. We have our z-dependent function, we have lambda CDM, and below that we have what I call the Friedmann equation, familiar to many of you, which removes light and dark energy from lambda CDM. Now, when you get rid of all the red terms in both models, you get a flat line tension of 9% across that Z domain. When we then accrete 16% of the baryons, that tension disappears, and these models give identical results over the entire domain Z equals 0 to 1089. The red terms give curvature, and that's shown here. All right, we have our light energy curvature on the right side, and then we have dark energy curvature on the left side. And that purple line at 1, that's what I call the Friedmann baseline. Okay? So that dark energy curvature arises from suprathermal kinetic energy in the intergalactic medium, which is mostly carried by electrons. Okay? These free electrons, they store more energy than gases do. They get real hot, they store energy as relativistic mass, and when they cool, that relativistic mass loss, E equals mc squared, well, yeah, that's a tremendous amount of repulsive entropic force and radiokinetic energy. Okay? I'm going to get picky, it's momentum loss. So we have two kinds of kinetic energy in the intergalactic medium. We have thermal and superthermal kinetic energies. My position here is that these thermal free electrons actually behave superthermally, and they belong on the right side of that equation at the top there. In fact, I think they're most of that energy. So we have to make an approximation here. We're going to say that all gravity uptake arises from thermal loss. That way, the adiabatic sphere does not change its size, and we can add the superthermal energy into the adiabatic sphere and keep it constant. So we have some substitutions here. We got more substitutions. These are busy slides. I just want you to focus on the gray box in the lower right-hand corner, okay? And also please note that that green accretion term, we hold it at 16% accretion or 0.84. That's a big if, but we have to do it because it's the only way that makes the model work at this present time. So, we calibrate against that gray box against lambda CDM. Point by point, we use 101 points from Z equals 0 to 2. You can use any Hubble constant, you can use any temperature. They all give the same graph points shown at the left, which returns a Lin-Lin line. Okay? Here's those results. There, finally. We get a pretty good, when we just include the scale factor as the x, as you will, we get a pretty good result, but it diminishes slightly out to Z equals 2, okay? It drops off slightly. When we include the red and green terms, we get an exact match out to lambdas, with lambda CDM out to Z equals 9, okay? This gives excellent correlation with lambda CDM all the way back to cosmic dawn. We're now going to look at that 2.24 into the square root, and it corresponds to about 58% superthermal kinetic energy in the intergalactic medium. Okay? When we throw in that gravity uptake term, it returns the dark energy density. Right? Now, it returns the dark energy fraction, my bad. Dark energy density is held as a constant under the model. Now, the DESI collaboration is challenging that, and I think many of us have seen those results they brought in just yesterday, right? Well, my model allows for and almost predicts that kind of behavior because its source is the cosmic web of galaxies, which is pouring energy into the intergalactic medium all the time. And that process maximized around z equals 2. Thanks. Well, at z equals 0, dark energy is 10 orders of magnitude greater than not just superthermal, but all kinetic energy in the entire universe. 10 orders of magnitude. Well, it's an artifact. The continuity equation showed here in its Newtonian form. It's one of the 3 equations used to develop lambda CDM. It in turn is derived from this bound expression of the first law of thermodynamics, which only describes what's happening inside a vessel and ignores the entire rest of the universe. So here's what they do. They freeze entropy for a freely expanding gas, and they allow total energy to change instead. These are both inconsistent with the thermodynamic laws. Their roles are reversed. And total energy is comprised almost entirely of rest mass today. When you plug the numbers into lambda CDM, it returns negative rest mass and repulsive minus mc squared. That's your lambda right there, and it's fictitious. The first law does not allow rest mass to change. Lambda CDM is an unscientific model which returns an unphysical value. My model is scientific, it is accurate, it is predictive in more ways than one, and it opens up a new frontier in theory for you young Turks. Okay, we don't have time for part 3, but we do have a little time for questions.
Thank you. Okay, thank you. We do have a minute or 2 for questions. And there's plenty of space up here if you want to sit down. Any questions?
All right then.
Okay, then let's thank Martin Johnson again.